phases of this investigation. In the first one, we did large-scale group screening tests, so we were just measuring mathematics ability and reading ability in the participating children in all of these schools. Just blanket tested everybody to have a very good sample of these two skills and their relations to each other, so how they related to each other. That was one question, you will see why. And we used UK standardized mathematics and reading tests, which are tuned to the UK learning context. So they are standardized based on the UK national curriculum, which is again important because there may be large international differences. If you use an American test in the United Kingdom, it may not work as you expect. And this is true for various countries as well. And then we selected various individuals for further assessment. So we actually tested, again, more than 120, except 115. So we had tested about this number of children further with 18 standardized tests. And these included further math and reading testing. You can see subscales of intelligence tests here. We tested their IQ as well, and we used two IQ tests, the Ravens, matrices, and the WISC. And we tested their working memory. This was an automatized working memory battery on a computer. Basically, we tested all of their working memory function, or which may be theoretically important. And we also looked at socioeconomic status, tested ADHD, and in a further phase, all of these children, or quite a few of them, nearly all of them, took part in further custom tasks and 9 experimental protocols. And then in another phase, we did electroencephalography and MRI with these children. So it was like an additional more and more investigations with one child. At the end, we had about 60 in this sample. We started with this large sample, and obviously, as we didn't have unlimited money, unfortunately, that's always very good for research, we had to narrow this sample further. And there were about 9 experimental tasks. So altogether, each of these children who took part in the whole investigation were tested for about 6-7 hours duration. So our objective, because, as I was arguing, mathematics is very complex. Am I okay now? Not good. So, as mathematics is very complex, that's what we expected. We wanted to test lots of skills, so to give a very holistic, very in-depth representation of each child, not only to focus something which we think a priori is important, but perhaps it is not. So we wanted to test everything. It's more of a data-driven approach, perhaps more fitting for the 21st century, I think. And here you can see the representation of all of the children in our sample. So this is all published material. You can read about this further in this learning and instruction paper if you want. This details everything in depth. You can see reading scores on this scale and mathematics scores in this scale. So these are standardized tests, which means that the population average is 100. So these children here are average in all of these, in both of these achievement measures. And if you move to this side, so these children are already very high achievers in mathematics, let's say. So the standard deviation, as usual in psychology test, is 15. So this is one standard deviation, this is 2 standard deviations on this test. So you can see that these children here are very high achievers in mathematics and reading as well. And then you can draw nice boxes over this population. For example, our primary interest was, so to say, this box, which had around 5.5% of the children, or 55 in this sample. Why was this the most interesting for us? Is because these children are low in mathematics achievement, but average in reading achievement. So reading could be used as kind of a control measure here. It reflects that these children are not generally poor in any kind of cognitive ability, but they are average at least in reading. However, they are poor in mathematics. And it's important to emphasize that we tested reading and mathematics twice in these children, and then ultimately we used the average scores from both testings to decide whether somebody is weak or strong in something. So, because if you just test once, then you may end up with some random scattering of test scores, but two test results can confirm more robustly that actually children are weak or strong throughout time. So it's not just a one-off result you are measuring and define as weakness or being strong. So, however, other boxes may be interesting as well. So, this reflects why it's important to test a large population of children, I think, which is rarely done in psychological studies. I think often people just shoot once, and then you grab 50 or 100 children from a classroom, test them. However, it's not clear whether you really have a representative population there. If we have a large sample, then we can test just a random sample of them, or draw children from this particular part of this distribution, or you may be interested in these children, let's say, who have very high mathematical achievement but average reading achievement, or these are average mathematical achievement children with high reading achievement. So all of them may have very characteristically different profiles, different strengths and weaknesses, probably very different cognitive profile as well. So it's interesting to study them further in detail. And one of the questions why we were interested in population distribution here was because lots of some researchers would argue that weak mathematics is more typical of girls, or dyscalculia may be more prevalent in girls. There have been arguments about this in the research literature, but not much actual data. And then if we look at the distribution of mathematics scores in girls and boys in this United Kingdom sample, so it's important again, this is coming from the UK, year 3, year 4 children. Then what you can see here is the mathematics score and the percent of children scaled to the maximum of to the overall sample of girls and boys separately. And you can see that the distribution of mathematics scores was about the same in both genders. So there was absolutely no difference between girls and boys in math performance. On the low end, you can see slightly more boys, but it's a non-significant result. So basically, there was no gender difference in the distribution of these scores, which kind of opposes this idea of more girls being diagnosed with dyscalculia or mathematical weakness. So we couldn't confirm any of these. And if anything, you can see that in reading scores in the United Kingdom, at least, we found more boys on the low end and more girls on the high end. And this is an interesting piece of observation. Okay. So an interesting piece of observation, because some researchers in past studies, and you have to be alert for this, define dyscalculia as kind of a discrepancy between reading scores and mathematics scores. But if you think about the fact that girls may be better readers than boys, then if you compute the discrepancy score between reading and mathematics, then you may find larger discrepancies, and actually that's the case in girls than in boys. And you may diagnose, so to say, some girls as being dyscalculic simply because they have a larger discrepancy between their reading and mathematics scores than boys. And this probably happened in some past studies, so it's important to consider this when you read the literature. So perhaps the classification of children were not the best. So these study of the distribution of math and reading scores definitely suggests that looking at discrepancy scores between reading and mathematics is not a good approach, but you have to look at absolute scores when you try to classify these children. Of course you can, yeah, lots of thoughts here. Yes, but the discrepancy scores we certainly not recommend for any kind of diagnosis or classification of children. And we had these numerous experimental tasks with these children, as I mentioned, so 9 experiments. It took like 2-3 hours to complete with each child. Basically, we looked at everything what has been proposed in the research literature as important. in dyscalculia, and the past research literature is fairly confusing. So if you are interested in this and try to read more about dyscalculia, then you will find some evidence for a lot of things. So nearly for everything being deficient. And for this reason, again, it's very important to test nearly everything if you want to have like an in-depth view of what is dyscalculia and how dyscalculic children differ from normally developing ones. Again, this is a published material here, so all of these investigations are described fairly much in detail in this Cortex paper. So as you see, we tested this very large range of cognitive functions in these children, and then first of all, you can see how one approach is to compare two groups of children, and that's what we did in this study, in this particular paper, as this is a very frequent approach in the research literature. And by this approach, you look at a control group of typically developing children and an experimental group of children with developmental dyscalculia, and the challenge is to match them very closely so that they are not really different on anything else, only on mathematical performance. And that was our objective here, as if you define dyscalculia as kind of a selective disruption of mathematical learning, selective disruption of mathematical understanding, then that is very important to make sure that the children in these two groups only differ in mathematics, or yes, they only show robust differences in mathematics, but not in other domains. And then you can look at their cognitive profile, and in this case, you can conclude that any kind of difference between their cognitive profile is indeed only related to differences in their mathematical achievement. So you can see the profile of our control group and the profile of our dyscalculia group here. You can see standardized scores on this scale, projected to 100 scale. So you may notice that the control group shows perfectly average performance. So again, 100 is the population average score here by standardization. And the dyscalculia group shows weak mathematical performance. This is our math score and the intelligence test numerical operation score. So these are very weak. However, performance on all the other scales were in the normal range, and whereas there was absolutely no difference between the control group and the dyscalculia group. You can see reading scores here. This is an intelligence test vocabulary score. This is a word reading score. This is a pseudo-word reading score. This is another intelligence test, Raven. This is another intelligence test for spatial intelligence, the block design test. Yes? So in all of these measures, these two groups were not different from each other, they only differed in the math performance. And then we looked at all of these experimental results to see, and test results, which are seemingly not necessarily related to math performance, and decided how children in these two groups are different in terms of their cognitive profile. And I have to emphasize that that kind of matching, so this matching is extremely unusual because it's tough. You have to have a large population. That's one reason we had 1,000 children, because you can really match your weak performers to appropriate control participants by a computer algorithm in this case, without the touch of a human hand, so to say. And this is very rarely done, yes? Yes, block design. Spatial computation, spatial intelligence in general, not awareness as such, just how. Sorry? It's not a spatial awareness in the way we measure it in math. No. It's a very technical test, so to say. But so that's the question, because we don't know how these exactly relate to mathematics. We use these here because it's frequently argued that you have to control for intelligence. So I'm not a big fan of intelligence tests in general, I have to say, because I think it's very undefined what they are actually measuring. They are like blanket testing. Again, lots of skills. They may include spatial intelligence, spatial awareness, but you do have to carry out computations. I think it's kind of a, in my opinion, I'm not a fan of intelligence tests because of this reason. They are not specific enough, in my view. So what we are actually measuring is always dubious. I prefer more specific tests. So, and again, all of this is published in this Cortex paper, if you want to read more about this, and it's fairly big testing range, so I'm not going to summarize all the results here, but the outcomes, if I just summarize the major outcomes, were that visual spatial short-term and working memory differed between typically developing children and control children, and the suppression of unwanted information was also weak in developmental dyscalculia, in children with dyscalculia, when they were compared with control and typically developed children. So you can see one representation of results here. This is a dot matrix score, which is a short-term visual spatial memory test, computerized. These are the scores from the so-called odd one out, or OOO, as we call it, odd one out test, which is a measure of visual spatial working memory. And this is the difference score between dyscalculic and control children. So it's a difference score. If you see that it's negative, it means that the dyscalculic children are performing worse than the control children or the typically developing children. So in this case, when you look at visual spatial short-term memory and visual spatial working memory, you can see that the short-term memory score, for example, was -10 scores lower in dyscalculia than in typically developing children, and this difference was there in visual spatial working memory scores as well. 95% bootstrap confidence intervals are shown here. So if these confidence intervals are not crossing into zero, according to this statistical approach, then you can accept this difference as kind of significant between the two groups, and the confidence intervals give a good impression of effect size as well. So you can see that we can say that visual spatial short-term memory and working memory scores were kind of robustly different between these two groups. So that's one look at the results. And here you can see digit recall, which is a verbal memory score, word recall, again a verbal memory score, listening recall, and listening recall, two different scores. These are verbal working memory scores. And these are hovering around zero, which means that they are non-significantly different in the two groups. So that was, for example, just point out at this, if you are more interested in the details, a very surprising result, because there is also evidence in the literature that verbal working memory is different, may be different in control and dyscalculic children. However, in our investigation, and we replicated this with 7-year-olds later, this has never been the case. We always only measured that visual spatial memory was weaker in children with dyscalculia than in control children. So we always found very specific evidence for the weakness of visual spatial processes, visual spatial memory in specific, but not for verbal one, which is interesting. It may have also to do with the content of the tests, because we used arithmetic operations tests as kind of a mathematical outcome measure, and some investigators may have used text problems or story problems, and you could expect more that verbal memory may be related to story problems, but perhaps arithmetic, the solving of equations, solving of symbolic problems, mathematically defined symbolic problems, that's what we found is more related to visual spatial memory than to verbal memory. It may also reflect teaching, though, so there are lots of questions. the content of the test, the education system you are working with, but at least in our UK samples, we always found evidence for the specific involvement of visual-spatial memory in mathematical processing. So it's important to keep in mind the potential culture and education system-specific aspects. And so this is one of the working memory tests used. So you see, or the children see a grid, and these elements, these dots are shown in certain locations, and then later in the sequential test, they have to recall each of the item locations in order. And in the simultaneous test, order doesn't matter, so they have to recall the locations irrespective of order. These are two memory tests, for example, we found important for, or to be very strongly correlated with mathematics skills, mathematic development. And this is an inhibition test which we developed in these particular papers, which we also found to be weakly performing in children with dyscalculia relative to typically developing children. In this case, children had to decide, let's say, which animal is larger in real life than the other one. You can see that the tiger is a bit smaller than the ladybug here, and this results in quite considerable confusion, not only on behalf of children. If you would do this task, then it's a Stroop task, basically. Even in adults, in grown-up adults, this results in confusion, so your decision times and error rates are much worse in this case compared to a case when the tiger would be larger than the ladybug. So this is a very simple non-verbal Stroop task, basically, which can be given to children, and you don't have to care about whether they can read or they can't read. So we developed this to work with young children. So these are two characteristics tasks. We found weakly performing in dyscalculia. And then we get to another imaging modality, electroencephalography. You can see this. This is the same net what I've seen here at this university, actually, so we've been using this since a while, and I don't have to ask for permission from myself, so I project myself here, just to, yeah. And electroencephalography is different from MRI, so it gives you kind of an impression of the electric activity of the brain. So it's measuring direct neuronal activity. It's measuring the electrical impulses which these neurons are sending to each other. So it's picking up some of these signals just by putting these electrodes on the surface of the scalp. And then in some appropriate experimental paradigms, you can conclude about the underlying mental functions which are important in a certain task. So with electroencephalography, you have a nice voltage map which you can project on the head. These are very fancy maps, but these are usually quite useless. For my practice, the most important representation is this relatively boring one, where you can see the voltage fluctuations in function of time, and then you can compare experimental conditions to each other and conclude about what kind of mental difference we have between them. And here are our typical participants in our experiments. You can see the effort you have to put into this child experiment when you want to convince children to behave very nicely, not to move too much. Don't blink in this situation. Then you obviously have to bring their friends to the lab as well and work with both populations at the same time. But we have very good experience, and motivating the children is the key, I think. So here you can actually see data produced by children participating in our experiments. So this is the neuroimaging phase, the electroencephalography phase of our studies. So that's a submitted paper, so hopefully you can read it soon, I hope so. So what I mentioned so far, I'm fighting my jet lag a little bit at the moment. what I mentioned so far is that we found that developmental dyscalculia is related to visuospatial memory and inhibition impairment in our population. So these were our observations. So we used the visuospatial memory task in the electroencephalography context with these children, so again 9 to 10-year-olds, in our investigation. And we looked at first, because there was not too much information about this, whether we can find a brain measure of working memory capacity in these children. And second, if we found that developmental dyscalculia is related to visuospatial memory weakness, the question arises whether we can confirm with electroencephalography that a brain measure of visuospatial memory capacity is also related to mathematical performance. That would be kind of further strong evidence to link the two to each other. Yes? And so here we use the relatively established memory task, which is a change detection task. Can you notice the difference between the two displays? Hopefully, yeah, that's the task the participants have to do in this experimental situation. So first they see these colored squares, and then after that they see this test display, and one of the squares may change color or it may not change color, and then your memory task is to detect this color change. Yeah? And if you detect the change, that we can assume that you could remember this display you've seen previously, but quite a few times people may miss this change. And we can vary the number of items in this display. You can see that there could be 2, 3, 4, 5, 6 items in this display, and in the test display, obviously, which comes after. You can see the error rate here and the reaction times here, and obviously the error rates and the reaction times are climbing up as we increase the number of items in these displays. That's a well-established fact. And previously, actually, there were no child studies at all with this experimental paradigm. So it was important to see whether the number of items in this memory display can be related to the brain measure of visuospatial memory. So you can see the voltage fluctuations in function of time. So it's the same display, same kind of representation, the useful one, which I've shown before. And then this is a condition where there were 2 squares on the screen, and this is the condition when there were 6 squares on the screen. And you can see that there is a large separation here at this particular time. 0 here stands for the time when this test item was presented. So after first we present this to be memorized item, after that you present the test, and 0 represents the time when the test item was presented. You can see that even before that we found already a difference in function of the squares you had to remember. Yeah, this is again kind of an established result in adults, and we could argue that this brain measure, this voltage fluctuation, reflects the amount of cognitive effort you put in to memorize these items, and we can expect that effort to be different in case of 2 items and in case of 6 items. So it's kind of logical to find a separation between these signals here. Though it's not evident that you can actually find them, but it's kind of an experimental observation that you can show that there is a voltage difference in function of the to-be memorized items in these displays. In adults, this has been shown, and this is first clear demonstration in children. And if now we project these voltage fluctuations on the scalp, yeah, you can see the coloring represents voltage here. This is +2 microvolts, -2 microvolts, and we had 129 electrode channels on the scalp. You can interpolate voltage differences between them and represent how these separations, for example, look like if you project them over the scalp. Then you can see that in these electrode groups, which are marked by these bold dots here, we can find a significant separation between the 2-item condition and the 6-item condition. So this blue color represents this kind of negative voltage separation between, if looking at the 2 minus 6 subtraction, so this negative voltage separation between those two conditions there. Yeah? It's kind of clear. So this voltage separation is kind of a measure of the cognitive, of the memory load in terms of brain function between these two conditions. Yes? And the important, so our first objective in this study was just to show this kind of effect in children, so we could identify a brain measure of memory load in this experiment. And the second question was whether this brain measure is related to mathematical ability or mathematical test achievement in these children. And if we correlate that brain measure, that amplitude separation, with mathematical achievements, then we find that over all of these areas, which are marked by these stars here, so about this area, yeah, the same area exactly, we find a significant correlation between math achievement and the brain measure of visual spatial memory capacity, memory load in the experiment. So that was our objective, and we could indeed demonstrate that the two are very tightly correlated, as could be expected based on our developmental dyscalculia results. So in these 50-something children, we could say that visual spatial memory capacity, not only behaviorally, but also when it's measured at the level of the brain, was correlated with mathematical achievement scores. And then you can look at, let's say, reading scores. So our reading scores correlated with visual spatial memory load measure. They were not, only in this one electrode, but that can be considered kind of an incidental finding if in imaging literature in general. And then they were not correlated with IQ, they were neither correlated with age. So we only found a tight correlation between visual spatial memory capacity and mathematical achievement scores, which demonstrates that our findings were very specific. So they were not just related to any kind of correlation between visual spatial memory capacity and any academic achievement, but they were very specific to the relation between visual spatial memory and memory load and mathematical achievement, which is important. So that's, again, some kind of a confirmation of our results. So what we found so far is developmental dyscalculia was related to visual spatial short-term memory and working memory disruption, and also the suppression of unwanted information was deficient in developmental dyscalculia as related to control participants. Yes, and we confirmed this in our imaging findings, and then all of these papers are basically reporting those findings, what I was talking here. And if we went a step further, and we could ask whether we can use our findings in kind of a classroom setting. So far I was talking only about this basic research aspect. And one question is then, if visual spatial memory capacity and mathematical achievement are so intercorrelated, then can we find any kind of real-life activities which involve visual spatial memory and also are related to mathematical achievement, and perhaps they are also fun for children, so they enjoy doing them, and on the long term, perhaps this can be used for boosting mathematical abilities in a play setting. And then, one thing probably everybody liked as a child, certainly did, that was one motivation for the study, is just constructing anything really. Specifically in this case we use Lego, but usually children like to play with these kinds of construction blocks or construction elements. So our question was that if we can assume that this kind of construction ability is related to visual spatial memory, then is this construction ability also related to mathematical achievement? And then this was tested in 7-year-old children. So this is again a published study. You can look it up in this learning instruction. Not my PhD student, passed PhD student because she took her exam 2 weeks ago. So she passed. So this is part of her PhD work. She's first authoring that. So in this study, we tested again numerical and reading skills in these 7-year-olds in the UK. We used the Raven's intelligence test to test for intelligence. And then we used working memory tests to test basically verbal and visual spatial memory in working memory and short-term memory as well. So these are the 4 tests we used from this AVMA battery again. And then the children also carried out this block construction task. And what we found, and this was a mediation analysis, is that Lego construction ability, and these are correlations here, so I won't detail the actual statistics. So Lego construction ability was related to visual spatial memory, visual spatial working memory, and short-term memory, to both. And if we did try to decipher the mediation pathways between them, then